So last class we talked about those measures of center and spread. For center, we had the mean, median, mode, and mid-range. Really the main ones are the three M's, mean, median, and mode. And we talked about the mean and the median being the ones that are the most useful for numerical data. And as long as everything is normally distributed or well distributed, they should be equivalent. They should be about the same number. If we have really skewed data, of course, the median is more stable. Then for spread, we had the range and the standard deviation. And we saw how that range was quick and easy, but not real discerning. So we tend to stick to the standard deviation for measures of spread. Like I said, for center, the mean or the median are pretty equivalent. What we're going to talk about today is we're going to go back to that distribution, that curve, that bell-shaped curve. And that bell-shaped curve has some standard characteristics that are extremely useful. First of all, the center of that curve, like we said last class, could be either the mean, the median, or the mode. We tend to use the mean or the median. We're going to just use the mean, because that's generally slightly more available than the median in most cases. And then we're going to use the standard deviation to describe the spread of that. We talked about standard deviation describing spread, but we didn't really talk about, well, what does it mean on this curve? Well, what it means is if we go out in steps away from our mean, and those steps are one standard deviation at a time. So like going to the right, this would be +1 standard deviation. And the next step would be +2 standard deviations and +3 standard deviations. And going the other direction to the left, it would be -1 standard deviation and -2 standard deviations and -3 standard deviations. And the breakdown of the data in those sections is very predictable. Between the mean and one standard deviation above the mean, we expect 34% of the data to fall in that range. Now, some textbooks call that 34.3%. It all depends on how you round it off. I'm using what's called the approximate empirical rule. Some textbooks use the exact, but it's still about that 34%. And then between one standard deviation and two standard deviations, we get 13.5%. And then between 2 and 3, about 2.35%. And then more than 3 standard deviations is 0.15%. If you add those all up, you would get 50%, which makes sense. That's just half of the curve. The other half is an exact mirror image of that. So 34%, 13.5%, 2.35%, and 0.15%. So really, what does this mean? Well, what it means is if you have a set of data where you know the mean and standard deviation, let's say for this class, let's say through the last 10 years of teaching this class, the mean final score is 84 with a standard deviation of 5. So what that would mean is the center here, the mean would be the 84. Standard deviation of 5, so if I go up here, I'd have to add 5. What's 84 plus 5? 89. Every step we would add another 5. 89 plus another 5. 94, and then plus another 5. 99. Going the other way, subtracting the standard deviation, we'd subtract 5. So 84 minus 5, 79. Minus another 5 would be 74. And minus another 5 would be 69. Well, what does that mean? Well, it means if I ask what percent of students would score less than 79. Well, here's 79 right here. Less than that would be to the left side. What percent? If I add those all up, I would get 16%. So I would expect about 16% of my students to score less than 79. What percent of students would score more than 94? Well, I look up here, here's 94, more than would be to the right. If I add those percents together, I would get 2.5%. I might ask what percent of students would score between 79 and 89. Well, here's 79, here's 89. Between them is those percents. If I add those together, I get 68%. So I can use this bell curve to make some predictions. Obviously, it's very likely 68%, or a little over 2/3 of my students, are going to score between 79 and 89 on that test. Well, these percents never change. Those are constant for that bell curve. Like I said, they might be adjusted by 1/10 of a percent or whatever, depending on what textbook you're using, but those percents are always the same. What changes are these numbers down here based on whatever the mean and standard deviation are of the set you're working with. For example, where could you possibly use this? Let's say you're going to buy a house and you want a 3-bedroom, 2-bathroom house, 3-bedroom, 2-bath. And you do some research. And in the area that you're looking, you find that over the last several years, of all the 3-bedroom, 2-bathroom houses that have been sold, the mean selling price is $142,000 with a standard deviation of $28,000. So what does that mean? Well, that means on our graph here, on our curve or bell curve, the center is the mean of 142,000. I'm just going to put 142 there. We go out in our steps of the standard deviation. We go 3 steps to the left, 3 steps to the right. It's always 3 steps in each direction. Going to the right, we're going to add the standard deviation of 28,000. So we're going to do 142 plus 28 is 170,000. The next one, 170 plus 28 is 198,000. And the next one, 198 plus 28 is 226,000. Going to the left, we subtract the 28,000. So this would be 142 minus 28 would be 114,000. Minus another 28 would be 86,000. Minus another 28 would be $58,000. And remember, as we said, those percents never change. This is still 34% here and here. These are still 13.5% here and here, and 2.35% here and here, and 0.15% out here. And let's say you find a house that's priced at 198,000. And your agent is telling you you better put in an offer right now. You find it, you really like this house. Your agent's telling you better put in an offer right now. This one's going to sell quick. Well, what this tells us, 198,000 is right here. If we look at that, if we want to know what percentage of houses are that price or above, well, more than that would be to the right here. We look at those percents, and if we add them up, that's 2.5%. What that's telling us is only 2.5% of all 3-bedroom, 2-bathroom houses that have sold in the last few years went for more than 198,000. Now, the other side of that, less than that price. We look over here. That's 97.5% if we add those all up. In other words, 97.5% of all 3-bedroom, 2-bathroom houses in the last several years have sold for less than 198,000, which means you've got two options here. One, the seller is most likely going to accept less than 198,000 for that house. And if not, there's a pretty good chance, since 97.5% of all 3-bedroom, 2-bathroom houses are priced less than that, that you're going to find something cheaper that you still like. Does that make sense? It's a very powerful tool in business when you go to analyze stuff. If you know, let's say you know that market-wide, most companies have sales, right there. Let's say most months you have sales of $64,000. You have a mean sales of $64,000 and a standard deviation of $8,000. So you want to set goals. So you make your curve, 64,000 goes in the middle. I'm just going to put 64. You go up by 8, so it's 72, 80, and 88. Again, that's just adding that standard deviation of 8,000. Going this way, you subtract the standard deviation, so you're going down by 8. So you got 56, 48, and 40. And those percents are still the same. So if you want to set your goal for the next month's sales, we could say, well, we want to hit 80,000 next month. Well, when we're looking at that, however, we realize that, there's only been about 2.5% of our months that we've hit 80,000 or better. That might be a little bit too high. I mean, that's still worthy to shoot a goal that high, but you want something obtainable. If you try 72,000, which you look at, that's only 8,000 above your average, but if you look at the percents, adding those up, there's only 16% of months where you've hit 72,000 or more. That's a reasonable goal of saying you want next month to be in your top 16% of your historical months. That's a little more reasonable than saying I want to be a top 2.5%. Or you may drop a little lower and say, hey, you know what, I just want to be above the 60th percentile or whatever. You can do that. I mean, this curve kind of limits you to steps of a standard deviation. If we had more time in here to go into more detail with something called normal probability, we would talk about how would you get between those standard deviations and how would you get those percents. This just requires more time than what we're going to take. Related to that, so this is allowing us to compare items and find percents within a population. So we're saying we're evaluating one single value and where it sits. This is evaluating a goal setting based on our previous history. And the other one, pricing houses or whatever. What if we have two numbers that we want to compare, but not two numbers that are closely alike? Let me show you what I mean by that. So when you came into college, you most likely took two placement tests at least. I know there's actually four I think you take for us right now, but let's just say you take a math test and an English test. And on the math test, you scored 58. And on the English test, you scored 72. Does that mean you're better at English than you are at math? Not necessarily, because those aren't the same tests. There's differences. So how can we compare them? The math test just may have been a lot more difficult than the English test. So how do we compare them? Well, what we do is we look at all of the people that have taken each of those tests. And we find the mean for the math test. We see that the mean on the math test is a score of 49 with a standard deviation of 5. On the English test, we find that the mean score is 60 with a standard deviation of 7. Well, we can compare them with something called a z-score. What a z-score is a way of comparing a number not to the other number, but back to its own population. A z-score takes the number we subtract the mean for its population, and we divide that difference by the standard deviation for that population. Let me show you what I mean. So for the math test, that z-score would be the score of 58 minus the mean of 49 and divided by the standard deviation of 5. So 58 minus 49 is 9. 9 divided by 5 is 1.8. What that is saying is your math test score was 1.8 standard deviations above the mean. If we're looking at this bell curve, this is 1 standard deviation, this is 2 standard deviations. That'd be somewhere in here. That's actually pretty good. If you look at that, it's probably only 7 or 8% scored better than that. We can't get that exact number off of this curve because it's not exactly on one of the standard deviations. The z-score then for the English test would be the score of 72 minus the mean of 60, then divided by the standard deviation of 7. Well, 72 minus 60 is 12. 12 divided by 7 is 1.7142857 approximately. We're just going to go 7.1 or 1.71. So what that's telling us is that score is 1.71 standard deviations above the mean, which means your math score is actually slightly better than your English score compared to the difficulty of the test. Another application of this, let's say you are managing a department store and you want to get rid of one of your salespeople. So you're going to fire a salesperson. You've got it narrowed down to 2 salespeople, Bobby and Stevie. And you decide whoever has the worst sales next week is the one you're going to let go. Well, next week, Bob has sales of $2,400. Steve has sales of $3,700. Well, does that mean Bob's out the door? Not necessarily. Let's say Bob works in toys. And for all of the salespeople in toys that week, the mean sales was 3,300. The standard deviation of $400. Steve works in electronics. Well, most electronics are more expensive than toys, so it makes sense that he would have more sales. Let's say for all the salespeople in electronics, the mean sales was 5,200. And the standard deviation was $500. So the z-score for Bob's sales was 2,400 minus the mean of 3,300 divided by the standard deviation of 400. 2,400 minus 3,300 is 1,100. Oh, sorry, a negative 1,100. Negative 1,100 divided by 400 is a negative 2.75. That means that Bob's sales is 2.75 standard deviations below average, below the mean. Bob did not do well. Well, let's look at Steve, the z-score for Steve. Steve's sales is 3,700 minus that mean of 5,200 and divided by the standard deviation for electronics of 500. Well, 3,700 minus 5,200 is a negative 1,500. Negative 1,500 divided by 500 is a negative 3.00. Steve's sales were 3 standard deviations. That's what the negative means, is below the mean. If it was positive, it's above the mean. Because the negative 3, Steve was 3 standard deviations below average, which means, sorry, Stevie, he's gone. That doesn't mean Bob's safe. I'd probably still be looking to replace Bob as soon as I can, because that's pretty bad sales as well. So it's a way you can compare numbers from separate populations. Where might this be useful for you? Let's say you have 2 job offers. Job offer A for $19.20 an hour. Job offer B, $21.60. Now, a lot of people would jump at offer B because it's $2.40 an hour more. But let's look at the mean pay, the mean wage in each of these areas. Let's say they're in different areas. Of course, cost of living can be different. So in the area that offer A is from, let's say the mean wage is $18.40 per hour. With a standard deviation of $1.20 per hour. Let's say in the area that offer B is from, the mean wage is $20.20 per hour, with a standard deviation of $2.10 per hour. So let's find the z-score. Offer A, or z-score, is going to be the 1920, that's the number, minus the mean of 1840, divided by the standard deviation of $1.20. So 1920 minus 1840 is 0.80, divided by $1.20 is 0.66666.67. So that's 2/3 of a standard deviation above the mean. It's a little bit better than average. That's not a bad job offer. On the other side over here, our z-score. We would take the number, $21.60. We would subtract the mean of $20.20 and divide by the standard deviation of $2.10. 2160 divided, or 2160 minus $20.20 is $1.40. Divided by the $2.10 standard deviation, that is 0.67. So those two job offers are exactly equivalent between those two places. Both of them are 2/3 of a standard deviation above the mean wage for that area. So in other words, the pay is a wash, so it's other considerations, neighborhoods, schools, stuff like that, whatever you're concerned with. That would be your deciding factor. Any questions? Okay. Tomorrow, we are going to review a little bit for test 4. Of course, test 4 is on Monday. There is a new quiz. It'll be due tomorrow, Thursday, at 11:59 p.m. And new homework due for Monday. I also suggest you start looking over the stuff from the last 4 or 5 weeks, because there is a lot of it. Remember, we had the areas, volumes, angles, measurement and conversions, feet to inches, centimeters to meters, all that stuff, gallons to liters. Okay. Then, of course, we had the statistics that we've done in the last few classes. Okay. Oh, cool. And then the graphing, graph the line or make the table plot the points. You keep mixing up the X and the Y. Remember, X goes this way, Y that way. Alphabetically, horizontal is first, vertical is second.